In this video, we continue with the discussion of arachidonic acid and its derivatives. We see in particular prostaglandins can be of different kind. We see that prostaglandins can also be transformed into thromboxanes. These prostaglandins will have all in common a 5-member ring with an R group attached that is 7 carbons long with a carboxylic acid group. These prostaglandins can have either an alkene ketone or enone, or it could be a diol, or it could be a hydroxy ketone. The X will designate what is the type of functional group present in that 5-member ring. More than that, we said in here that if it is the PGA, PGBs, and Cs, they are all alkene ketones with a different double bond in different positions. In this discussion, we are also looking for what is the mechanism for the synthesis of the prostaglandin from the arachidonic acid. This chemical reaction will start with the free radical from the amino acid tyrosine. So we have here the amino acid of tyrosine. See the carboxylate group, the amino group, and the OH. So the free radical of tyrosine is the one that is going to initiate the reaction by having, because we know that free radicals are excellent about breaking bonds. So we're going to have the Fischer hook to break a bond. So from this free radical, we are going to have one of the 2 hydrogens present is going to be broken down. We're going to keep one of those 2 hydrogens, and that will be on carbon number 13. So now we have only 1 hydrogen left, and that has become a free radical. Once the free radical has been formed, so we say that in step number 1, C13 becomes a free radical. That is after the reaction with tyrosine, and tyrosine will become protonated like it is in here. On the second step, the free radical of carbon 13 breaks the double bond between carbon number 11 and 12. So we're going to do the same using Fischer hook. So we take half the arrow and 1 electron in, and then carbon number 11 will become the free radical, and we are forming a brand new double bond between carbon number 12 and 13. So we still have the other double bonds. Now this free radical that has been formed now will be reacting with a molecule of oxygen that is attached to an iron center. So let's say that we have an iron center, like in hemoglobin. We have seen that hemoglobin has oxygen bound, but we have now this free radical that is going to make a covalent bond with the iron that is being provided. So we say here we have a brand new bond, and after this step, I'm going to have to do the drawing to finish up. We're going to say that this other singlet from the oxygen is going to break the double bond that is between carbon number 8 and 9. So let's do that one as well. So after we said this was step number 1, form the free radical that is going to break carbon-carbon double bond on 11 and 12. The brand new free radical is going to form a bond, and now we are going to break one more. Now we have 1 electron left that is going to break, that is going to make the 5-member ring, and that is, we're going to say just now with this long electron left, we're going to do the same, breaking one bond. So we have here the formation of a brand new one. Now this last electron that is left here will be the one reacting with the one on carbon number 14. So we have a brand new bond, and then the last one here is the one that is going to react with a second molecule of oxygen that is attached to another iron center. So we have a second iron center that is going to provide the formation of a peroxide. So once we have done all of this cascade, we're gonna form a 5-member ring, and on this 5-member ring now we have attached 2 oxygens, and that is on carbon number 9 and carbon number 11. This was carbon number 8 and this was carbon number 12, and therefore we have left carbon number 7, 6. Okay, and we have the rest of the molecule that has not reacted at that point. And from this point we also look at, we have formed a brand new double bond. We also have a peroxide, and that peroxide that is attached to iron is going to become protonated by tyrosine, providing back the hydrogen that was taken at the beginning of the reaction. So we need to count the carbons. We need to have 20 carbons long. 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 carbons long. And in this case, we have concluded with the synthesis of prostaglandin with the 5-member ring.